Thank you so much, Sarah, and thank you for inviting me to come here today. Let me dispel one myth right off the top. I am not an expert in physics education. My training is in medical physics, and I'm a researcher. I have been a researcher in that field for many years. I've kind of stumbled my way into the world of physics education, and I consider myself to be an informed educator. So I try to stay abreast of physics education research and use that. I'm a practitioner, and perhaps more that than an active researcher in the field, but I am here to share some of the things that we've been doing at the University of Guelph over the last many years. And before I start, rather than leave this until the very end, I want to start right off the top by saying the things I'm about to tell you are not all me. There's only one of me. I can only do so much. And I have an amazing team of people at the University of Guelph that I have had the privilege to work with over many years. I've been there, 20 years now. Is that right? Yes, 20 years now. And there have been many people that I've had the privilege to work with over those years. So the people in the white font are faculty, staff, either physics, math and stats, as you see, chemistry, open ed, as Dale knows, is what we call our teaching and learning support people. And then all in the yellow font on this column, so the top two are in white and then the lower ones are in yellow. They are all the students that have worked with us on various projects as undergraduate research assistants over the summer projects, or some of them as fourth-year research projects. So there's a lot of people involved in this, not just me. So I'm going to kind of give you a little bit of a sense of three main things that have been a focus for me over the last few years, many years. One, I'm going to talk about first-year teaching, how we do it at the University of Guelph. I'm going to talk about science communication course, which is something that has been a passion project of mine for quite some time now. And I'm going to end with a little bit of lessons from the pandemic and how I approached things as we all did, trying to figure out our way of teaching in a brave new world. So, starting with first year teaching. So, Martin Williams was here, right? Several years ago. How many years ago now? I don't know. A few? A healthy few? Okay, a healthy few. And he's coming again soon, I hear. As one of the external reviewers for your undergraduate program. You couldn't have picked a nicer guy to be one of your external reviewers, I have to say. So I think you're in good hands with Martin. Martin probably told you a little bit about IPS, so I won't go into too much detail. But at the University of Guelph, we have different streams of courses depending on what the students are in. So for students who are entering in physical sciences, they take IPS 1500 in the fall and IPS 1510 in the winter. This is a double credit, so each one of those is a double credit course because it incorporates all of first year physics and all of first year calculus into one course. So it's double credit hours. It's 6 hours of lecture a week instead of 3 hours of lecture a week. It's the physics lab, it's the math tutorial. It's all in one package, and it was developed, the math and stats person who was on the screen, on the previous screen, was Dan Ashlock. He unfortunately passed away not that long ago, but he was an incredible colleague. It was actually his project that he came to the physics department and said, you know, I'm hearing that students aren't really prepared for their second year physics courses in terms of the calculus that they know how to do, and I think we could do this better. And I was like, yeah, that's a complaint that has been there since the dawn of time, so let's figure out a way to solve that. So we created this double credit course working closely together to develop it, and it's co-taught by somebody from physics and somebody from math. So the motivation, I already told you, to be better prepared for second year, and to give the math students some context for what they're doing, right? So to give the physicists the tools that they need to solve the problems and to understand the concepts, and to give the math students some context for why this is cool and why they need to be learning it. So the course is structured, this is the fall semester course. It's structured around themes. So we spend a couple of weeks talking about being a scientist, natural phenomena, sports, and wrap up with space travel. And then in terms of the way they go about things, we have case studies that are associated with each one of those themes. So I think you can probably guess which theme this one is the case study for. It's not space travel. It is the sports one. So this is based on a paper from the physics teacher in 2000. It's the kinematics of long jump. So what they do, working in tutorials in groups, is they take a mathematical model and try to predict the maximum range and launch, optimal launch angle for someone who is executing a long jump, which is really just projectile motion. But is it really just projectile motion? No, there's a lot more to it. So the first iteration of the mathematical model is pretend this person is a projectile and do the calculation from first year kinematics of what the optimal angle is and how far the person would go, making some assumptions about how fast the sprinter can enter the region where they're going to take off. And it turns out that the maximum range is a little over 14 meters. Well, that's not realistic at all, because the world record is 8.95 meters, and that world record was set in 1991. That's a long time ago. So that record has not been broken for what? 30 years. So that's 14 meters? Like, nobody's gonna set a long jump of 14 meters. So clearly, we need to fix this model. We need to improve the model. So the second iteration is taking into account the fact that, you know, there's things like air resistance, and there's some energy that goes into you running horizontally and then launching yourself vertically. So taking those things into account, that comes back to a much better, much more realistic maximum range in about what we see for the world record. And then the final iteration is to take into account the fact that the person's center of mass ends up lower than where they started, because they were running and then they jump and then they land lower than their upright position. So that's taken into account as well. So this has been running, this course, this sequence of courses has been running for a while now, good 10 years, I would say. And it has been very successful in terms of, I've taught the second year E&M course for many years, before and after, and I can certainly say anecdotally that there has been a change in the vector, or the ability to discuss things with vector calculus in second year E&M. When we first did this, it's very hard to do studies in this kind of thing, to look at efficacy, right? Because you need a control group. What are we going to do? We're going to have some students who don't do this and some students do. Well, are they taught by the same person? Are they in the same room? Is it the same mix of students? Are they as engaged? Are there as many questions in a given classroom? There's all kinds of things that you can't control. But we had the opportunity to see something of a difference between two groups of students, because when we first introduced this course, the university was very worried about, Dale's smiling. The university, you probably remember, you remember? Yeah. So originally, the IPS courses were supposed to be 3-in-1. We got funding from the provost's office to develop chemistry, physics, and calculus all together. And that was hard. It was hard. It was great. It was gonna be amazing, but it was hard. And then, but there was a lot of concern all the way along that, oh my goodness, there's too many eggs in one basket, 3 credits in one. What if they fail? What if they drop the course? There were all legitimate issues. We designed the course, we thought, to accommodate those concerns. It was approved, that said it, and then it was yanked because they didn't like the idea that it was 3 credits in one. So we went back to physics and calculus, which we could have done over coffee. Well, okay, maybe not, but it would have been a lot simpler. But there was still concern, even when it was just the 2-in-1. So for the first year that we ran, they still wanted us to run the 2 separate courses and let students choose whether they wanted to do this crazy new thing of physics and calculus together or do them separately. So Physics 1000 was the fall semester mechanics course that we had taught for a million years and was the basis of the IPS course. So a bunch of students, it was about 50-50 who chose the newfangled thing and who stuck with the tried and true. And so we did a pre and post. assessment using the force concept inventory. I don't know if you're familiar, but this is a standardized multiple choice conceptual questionnaire that you can administer to your students to get a sense of their underlying knowledge of basic mechanics concepts. And we did it before and after the course, like the first day and the last day. And the results from Physics 1000 were not good. The incoming average on day one was 38%. And then at the end of the semester, it was 45. So it went up, but not significantly. And the numbers, that was just who was in the class on that day, really. So IPS 1500, the incoming average was 57%. Now that's something that we need to talk about in a minute. So the incoming was 57%. The average at the last day was 69%. That is a significant improvement, hooray. And looking at, qualitatively looking at those red bars, some encouraging sign that it is shifting over in the right direction. Now, this comes back to my comment before, it's really hard to do these studies because there's an issue right there in the selection, right? And you've already guessed that because the incoming average for the students who selected the tried and true thing was 38%. The students who selected the new crazy idea of physics and calculus together was significantly higher. So they're not the same group of students. We're comparing apples and oranges. The best thing that we can say from this information to the administration was, we're not doing any harm. First rule, do no harm. So we're not doing any harm with our new crazy fangled idea. And so we no longer run Physics 1000, and everybody goes into the 2-credit course combined. So that's a small group of students at the University of Guelph. Physical science course is usually about 200-ish, 150 to 200 students. That's small. The University of Guelph is a big life sciences institution, and we have about 1,500 to 2,000, so a factor of 10, more students in first-year biological science who take 2 semesters of physics with us. So how do we tackle that? Now, this is a problem that a challenge that I'm sure is true here and everywhere else. A good fraction of the students entering the University of Guelph do not have grade 12 physics. I'd say about 60% of them do not have grade 12 physics. And they have to do 2 semesters of physics for their degree. So we have created a course called Physics 1300 that they take in the fall, and then they take Physics 1080 in the winter. For the students who have done grade 12 physics, they don't need to do that kind of quasi-hybrid thing. In the fall, they do 1080 in the fall, and then they do 1070 in the winter. And like I said, it's about 60-40, about 60% of them need to do 1300 and 1080, and then 40% do 1080 and 1070. So the content for Physics 1300 is fairly traditional. So it's a lot of text, I know, but it's just like the main topics that we cover in Physics 1300. You're going to recognize almost all of those as things you probably do here, or you did wherever you did your undergraduate degree. Their kinematics, their dynamics, their forces, Newton's laws, electricity, those kinds of things, basic circuits. And then at the very end, we start to talk a little bit more about applications to medicine by talking about radiation, radioactivity, dosimetry, and some medical applications. Because these are all biological science students, so we're trying to find a way to connect what we're doing in the classroom with what they're actually passionate about. But it's more than that. It's not just trying to find ways to connect with them in terms of what they're passionate about. It's also how they feel about being in the classroom. These students have put off taking physics as long as they possibly can. They didn't take grade 12 physics, and about half of them didn't take grade 11 physics. They've taken no physics. They took grade 9 and 10 science, which has like a little unit of physics in there somewhere, but that's it. And they have been putting this off until they've been told, nope, sorry, you want a degree in science? You're gonna have to do 2 semesters of physics. So I've taught this course many times, and I always ask this on the first day. Any guesses on what this distribution is going to look like? My first clicker question of the semester. Are they excited? Are they ambivalent? Are they terrified? So I do the quick clicker question, and I put up the results, and they all laugh. Because there's exactly 5 students who have said they're excited about this. And this is 300 students. So it's about a 50-50 split among the rest of them between ambivalent and terrified. And I do this at the beginning of the semester for a bunch of reasons. 1, it's a great icebreaker. 2, it helps them to see that they're not the only ones sitting in this 300-seat lecture hall feeling absolutely petrified about what's going to happen over the next 12 weeks. Plus, I also take this as my opportunity to explain that I view my role as being the chief cheerleader in this course. If I can convince them by the end of the semester that it's not that bad really, and they're actually kind of enjoying it, and they're kind of seeing the relevance to the things that they find interesting and the things that they observe in their everyday lives, then I consider my job to be done. So that's the 1,300 students. We then, from 1,300, go into 1080, and then 1080 is also run in the fall for the students who did grade 12 physics. So 1080 is pretty different from a standard first-year physics course. We do forces and torque and kinematics and momentum, rotational motion, yada, yada, yada. That's great. We also do a whole bunch of stuff that is really not very standard, but it was designed many years ago with faculty in the biological sciences to find ways to connect physics to what these students are interested in. So we talk about pulsatile blood flow, and we talk about aneurysms and pressure and how that develops, and we talk about diffusion and osmotic pressure. And that means that we have to design our own resources, because there's no, you go to Survey or you go to Giancoli or whoever, they're not going to talk about this stuff, right? So these courses have been developed over the course of, I don't know, 20, 30 years probably, and we've had to develop all the resources from scratch. But the students find it to be a much more engaging experience because it's not blocks sliding down inclined planes and pulleys and all of that stuff. It's stuff that they're actually really interested in, and there's some cool physics in it. So why not cover that? So then 1070 is the course that the students who have done grade 12 physics do in the winter, and it also has a bunch of regular kind of standard stuff, but then we also do stuff like talking about how the ear works, talking about how vision works, talking about how corrective lenses work, talking about biologically relevant molecules like chlorophyll. How do they absorb energy, and how do they transform, and all of those things. The way the course is structured, it's usually in a 300 or 400 seat room, so we divide them up into multiple sections. That's a little bit historic because in our physics building, we have a lecture room that seats 287 students, and we have a lecture room that seats 150. And it looks like this. It's a little bit bigger and whatever, but it looks like this. And underneath, where everybody is sitting, is where we store all of our physics demonstration equipment. And there's a door right here where we can wheel it out right into the classroom and do as many lecture demonstrations as we possibly can. So that's these 300. So we always took our, let's say we have 1,500 students, well then we split that up into chunks of 300. The university used to prioritize scheduling us in that room. And then a few years ago, they decided, no, that was too complicated. So we don't get priority in that room anymore. So unfortunately, that means we don't do demonstrations as much because as I was talking with somebody, I can't remember who it was, it's not so straightforward to take your Van de Graaff generator and trek it across campus, unfortunately. But when we can, we like to make sure we do lots of demonstrations. We typically do this in the, I like to call it the POW method. Predict, observe, why. Predict, observe, explain, but that's not as good an acronym. So predict, explain, observe, why. So you set up what you're going to do, ask them to predict it, observe what happened, explain it, all of that. Do lots of things. I'm sure all of the things that you are doing too. Think, pair, share discussions with clickers. Clickers, top hat, whatever device you want to use. And then the way we structure the course is they have weekly online homework or pre-tests. They write the pre-tests or the online homework. They get multiple attempts at that. Once they pass that, they can then go and write a quiz. Used to be they'd get multiple attempts at a quiz. That's no longer the case. They only get one attempt at the quiz now. But the pre-tests, the quizzes, they're hand-marked, they get some feedback, and then there's the final exam. They also have 5 experiments to do. Used to be, again, that the 5 experiments were like the ticket to get to go to the quiz room. I know that doesn't sound like a treat, but that's the part that got marked, so they needed to go do that. So the labs are now actually largely done off campus. So this came out of the pandemic. The team at U of G, not me, I was not involved in this. Mike, Massa, Orbax, Martin, who else? Chris probably, designed lab kits that students bought at cost that were shipped to their homes wherever they were during the pandemic. And all of the experiments were done at home, and they uploaded the reports. So they used Firefox. Have you heard of Firefox? It's a smartphone app. Really great. It's got like frequency analyzer, it's got accelerometers, it's got pressure, it's got like all kinds of things that you can do with your phone. So for example, what was one of the experiments they did? They were, you know how when you're pouring water into a glass and you hear the pitch increase, right? As the air column gets shorter, you can hear when you're pouring the glass, right? Did you hear that sound? So they actually did an experiment where they had students pour water into the glass and record the frequency with the frequency analyzer on Firefox, and then they plotted wavelength versus air column height and got a pretty decent slope of 4. Yeah, I think it's supposed to be 4. And like things like that. So again, trying to connect the physics concepts. Yes, we talk about standing wave patterns a lot in one of the courses, but actually, you know, how many of them have actually stopped to think about that sound that everybody knows, everybody's heard, but have you ever really stopped to think about why it does that? And here's your quantitative measurement to verify that that's why it does that. So that's what they've been doing with the labs in that course. So where's Anne? I put the gamification back in. We were talking at dinner last night, and apparently, yeah, so I'd taken something out, but I put it back in. So, so they do these online pre-tests, and they're pretty, you know, bare bones. They're like, I don't know what learning management system you use. I think we decided it's maybe the same in the background, but you call it something else, and we call it, yeah, it is. It's D2L. Yeah, so we call it CourseLink. You call it OnCue, right. So it's, you know, it's nice. It's fine. It's kind of vanilla. It's like, you know, basic. So the pre-tests are done through that. We had a master's student, Jordan, who decided he wanted to explore the role of gamification to see if there was a way to engage students with the educational content in a fun way that in some way enhances the motivation to get engaged with this activity. So what he did was he partnered with a friend who was working at Boom Media, Digital Media in Waterloo, just down the road from us. And they designed a gamified interface for the pre-tests. So it was the exact same question. Here is, let's check the air column. Here is an air column of this length, and I've generated a standing wave of the second harmonic. What is the frequency of the harmonic, right? Exact same question, multiple choice, boring, sorry, D2L, interface, regular interface, and gamified interface, okay? And see what happens in terms of the engagement. So what does a gamified mean? It means that instead of getting a mark, instead of saying 1 out of 2 you got correct, you got points, okay? And the points were tallied in a gamified way. So it mattered on how many questions to this point you had gotten right. So the number of points you got for that question depended on how many previous questions you had gotten right. And it also depended on how many you had gotten right in a row. So it encouraged streaks. So it also was trying to decrease the guessing, right? So if you've gotten 3 right in a row and you're on the 4th question and you're not sure, well, maybe in the normal version you just click C. But now you got this streak in the balance. So maybe, just maybe, you're going to open your textbook, double check that that's the right answer before you click C, because you don't want to blow your streak. Now maybe it doesn't matter to you, and maybe this only resonates with certain students. But so the points were more elaborately calculated. There were badges for certain achievements. There was a leaderboard that you could choose to participate in or not. That was entirely up to you. And you got stars for how you did on the quiz. So if you passed, you got 1 star. And all you needed to do was pass to get a ticket to the quiz room. Okay? This wasn't graded in the sense of it didn't contribute directly to your final mark. You had to pass the quiz at 60% or more, and then you could go and write a quiz that was going to be graded for your final mark. So if you passed, you got 1 star. If you got a little bit better than pass, you got 2 stars. If you got perfect, you got 3 stars. And you got 1 question at a time, and you got instant feedback on that question. So depending on how you answered, you'd get a little text box that would say, awesome, great, you did it right. Or you'd get a question, you'd get an answer like, maybe you should check those units, or something, right? And so we made it optional. Students could choose whether they wanted to do the normal version or the gamified version. And Jordan compared the outcome. So there is a paper in physics education that came out in 2016. So if you want more details, please have a look. But one thing that Jordan noticed was that there was a big difference in the students who were doing the gamified version of the number of times they continued to do the pretest after they had passed. So they passed, they got their ticket to the quiz room. That's technically all that matters for the course. So they don't need to ever do this pretest again. But for the students who were doing the gamified, on average, there were multiple attempts after they had passed, continuing to play with the interface. So that was one thing that he noticed right away. And then the other major thing that he noticed was that the number of students who continued to do the pretest until they got perfect, way after they already passed it, huge difference between the students who had the regular version and the students who had the gamified version. Like huge. Like we've got like 15% of the students doing this pretest over and over and over again until they get perfect. Yes?
I'm curious if how many attempts did it take them to get a pass between the 2 groups?
Oh, good question. It was, the gamified version was slightly harder. Jordan did look at that. It was slightly harder, not a ton, but slightly harder. It did take, on average, slightly more attempts to get a pass in the gamified version. And we speculated that could have been a couple of things. One, it could have been that in the gamified version, they only got 1 question at a time. And once they answered and submitted, that was it, that was the answer. Whereas in the non-gamified version, they have a whole list of every question on the screen. They just scroll, and they can click it, and then they can change it. So when you've got, like, let's say you've got 2 or 3 questions that are kind of similar, you do the first one, you maybe guess wrong, but then you do the second one, you're like, oh, wait. So you could change your answer in the non-gamified version. There was another factor, I'm blanking on it right now. But yeah, it was a touch harder. Oh, I know the other factor. The number of points you get per question is not the same, because in the non-gamified version, it's 1 point for every question, no matter where the question is in the quiz, right? But for the gamified version, the number of points that you get potentially is more for a question that's later in the quiz, because if you've got a bunch right up until that point, you're going to have more points per that. So it was a little bit that too. But Jordan had to play around a lot with the algorithm that he was using for that. So it was a scooch more difficult, but not hugely more difficult. Good question. So the perfect thing, it seemed to be really all about those 3 stars. So you only get the 3 stars if you get a perfect score. And your star status is displayed on your user profile. It can be. You can choose to have it. Now, obviously, if you have 3 stars, you're going to choose to display it. But Jordan actually discovered this accidentally. So the formula for figuring out how many points you need to get, how many points you would get if you answered all the questions correctly is not like there's 19 questions, therefore the answer is 19. You have to figure out the maximum number of points you're going to get for each question and add them all up. It's not hard. It's just that one time Jordan goofed and he didn't calculate right the number of points that you need to get 3 stars. So he was like looking at the output one evening, and he noticed there were a whole bunch of students who were doing the pretest like 15, 20 times and answering all the questions right, but still doing the quiz. And he's like, what is going on? And he realized that he had calculated it wrong. So the students had gotten perfect, but they didn't get their 3 stars. So he fixed it right away, like 2 o'clock in the morning, he fixed it. Nobody else had to suffer the same heartache. But it certainly did say that, I mean, it's silly in a sense, but it's psychology. And those 3 stars actually really mattered. There's also a badge that if you got 3 stars on all of the pretests, then you got whatever high flyer badge it was, right? So maybe this is silly on some level, but it's also finding a way to encourage students to continually engage with a learning exercise. So I don't know, maybe that's not such a bad thing. Okay, so that's first year physics. I've got 2 more things to talk about. The other things will be briefer, I promise. So I was the associate chair of the department for about 10 years. And during that time, we had our review, as you're about to have. And it was a great review. We had great feedback. There were a bunch of things that were highlighted by the reviewers that you should really think about. And as the associate chair at the time, I'm like, yeah, really, we've been thinking about those for like 10 years now. Thinking about and not doing anything. So we blew up the curriculum and we put it back together again. And we created 6 new courses. We removed 5. About 9 other ones were fairly significantly changed. And it all started rolling out, I'd say, about 2015 or so. And a guiding principle was looking really closely at the learning objectives or the learning outcomes of our program in the physics department, at the Bachelor of Science level, and at the university level. And at the university level, there are 5 key learning outcomes for all undergraduates at the University of Guelph. And one of those 5 is communication. And we were doing, I would say, a pretty good job of teaching our students how to communicate very technically. They could solve problems in quantum mechanics, they could write a lab report, they could give a conference level presentation perhaps, but we weren't really doing anything about this, which is the description from the University of Guelph. Interacting with a variety of individuals and groups, communicating in a variety of formats. So we created a new course, Science Communication, which was all about communicating to non-technical audiences. So this is what I like to call how to evoke fear and loathing in physics majors. Because a lot of people don't like the idea of public speaking. This isn't exactly public speaking, but So this is a XKCD comic about the probability of the things that you study will kill you. Studying gerontology, yep, pretty high. Public speaking, yes, we may all be terrified of it, but it's actually not going to kill you. So, the course structure. This is two of my students giving a little talk about vectors to target audience was elementary school students. So they're dressed up as vectors. I don't know, you can't really see from that angle, but they've got like a red arrow on their heads. And that is, anyone who's that on the screen? Victor Vector, who is a villain from Despicable Me. And why is he called Victor Vector? Right, because he commits crime with direction and magnitude. Yep. So anyway, so that we have weekly discussions. We listen to a podcast, we read an article, we watch a video, and we talk about it. We dissect it. They are expected to do 3 presentations. The first one is, the acronym there means 3-minute thesis. So the idea is the 3-minute thesis structure. They have 3 minutes. They can have 1 slide. They can choose whatever topic they want. They're in 3rd year, so they don't have a thesis. They can choose whatever topic they want in science, any science. And they have to tell us when they start who their target audience is. So it could be the person you're sitting beside on the airplane, or it could be your grandmother, or it could be a kindergarten class. Whoever your target audience is, non-technical, you have to tell us who your target audience is and then give us your 3-minute talk. They do podcasts together in partnerships, and they do video presentations. They have 2 writing assignments. One is a pitch of a story idea to a newspaper, and then the other is the story. And then they have a group project at the end. All of these presentations, we do peer evaluation. I also give them feedback. The TA gives them feedback, and we do People's Choice Awards for the 3-minute thesis and the podcast and the videos, and it's a lot of fun. So Rob, I was having dinner with last night, among others, and he was asking me about improv. So the 2nd class of my science communication course, I spend the entire time doing improv exercises with them. And when they walk in the door, they're like, you're what? No, I'm not doing that. And Rob said he really wanted to come down and help me do some improv exercise. No, I'm kidding. I would never, ever force anybody to do that. So in my class, I make it perfectly clear that this is why I'm doing this. So it's all about encouraging them to be more spontaneous and less formal in their presentations. Is to be able to learn how to read body language, as I'm trying to do right now as I look around the room, and read nonverbal cues from the audience of whether they're engaged, whether they're confused, whether they're falling asleep, whether they had a bad lunch. And it's also about attentive listening when you're communicating with others. So these are all the skills that improv helps us develop. Plus, they're also really great at helping us to build a community. Because this is a class where they just came from quantum mechanics and they're about to go to, I don't know, differential equations 2 or something, right? And they walk into my classroom and I'm like, okay, so now we're going to talk about how you feel about that podcast we just listened to. And they're all like, what? I don't know. So there's a lot of trepidation about talking about something that doesn't have a right or wrong answer, because it's not really, as physicists, what we're trained to do in the classroom. So the improv exercises also helps to feel a little more comfortable with the class as a community to have these frank discussions to argue points back and forth. So these are some of the activities we do. They're chunked. The first 3 are low risk. That's the terminology from improv. They're low risk activities. They're done all together as a class. So word association is, I say the word bananas, and the person beside me says the very first thing that comes to their mind without thinking at all. Yellow, exactly, right? And then the next person says the next word that they think of when they hear the word yellow. But they're not supposed to be thinking about bananas anymore. They're supposed to be thinking just about the word yellow, okay? And we go around the class going as fast as we can. The only thing is you can't say a word that's already been said. So you do have to be paying attention to all the words that have been previously said. So there's a bunch of other games. So that's that one. Then we break up into groups, 2s and 3s, scattered all around the room, and play individually as little groups. So one of them is breaking news. That's a very popular one. So in groups of 2, I pretend to be a reporter on the scene in a lab where something very exciting has just happened, and I'm reporting with the expert, who is my partner, and they're telling me what just happened in the lab, and it's completely made up and silly, but it's that kind of game. And then the third chunk of exercises is if I have some brave volunteers who want to come and play a game like Rob was volunteering to do in front of the whole class. And one of those is the 3-headed expert. So that's a photo of my 3-headed expert there. It's Rafael, Melanie, and Joelle. And so the game there is I pretend to be Bob McDonald from Corks and Quarks, and I'm interviewing an expert on rocket propulsion or something. And the expert can only answer one word at a time. So I say, hi, welcome to Corks and Quarks. I'm Bob McDonald, and today I'm joined by Dr. And they can only say one word at a time. So tell me about this latest development you've discovered in this. And they're like, well, Bob, and it gets silly. But anyway, the writing assignments, as I said, they do a pitch to the Guelph Mercury Tribune, and then they write the full story. I'm the editor, and actually we have had them published, not all of them, but a bunch of them. And then the group project is in partnership with the Guelph Civic Museum. We run a thing called STEM Week, which is STEM stands for Science, Technology, Engineering, and Math. It is the last week of the semester. The students break up into groups, like 2 to 6 students per group, and they get a budget, $200, actual money that they can spend to design and build an activity for visiting elementary school students to do. And they have to tell me what they're going to do, and I dole the money out in small chunks, otherwise I don't get my receipts. Learned that the hard way. But they are just, it's so amazing to see what they come up with. And then we take everything downtown to the Guelph Civic Museum, and we had, the first year we did it, we had over 700 elementary school students come through in the span of a week to play with the activities that my students developed. So this is a group of students playing with the catapults that were built, and remarkably, I was running the catapult room, not a single finger was pinched the entire week, and I really did not think that was going to happen. So we go on a field trip to the museum, they see the space, we talk to the experts, and it's very carefully structured to make sure we're ready at the end of the semester. We have a dress rehearsal on campus, so the whole department and anyone else who wants to can come in and see what our amazing students have built or created for our students at the Civic Museum. And this is like a 2-minute thing on the first year we ran. And it's actually going. so the feedback from teachers was great. Honestly, good to excellent in pretty much everything. A couple of fails in the alignment with the curriculum and inquiry-based learning, but you know, frankly, these are third-year physics students who are designing these activities. They're not pedagogical experts. So I was happy with how that all came out. I will read this. Quite honestly, I was very impressed with this program. It was well organized, engaging in the perfect amount of time. The individuals from the physics department were incredible. They worked so well with the students and truly made sure the activities were suited for their age. Weeks have passed and my students are still talking about their experiences. Many parents have contacted me to let me know how much their children loved it. I'm truly hoping the program runs again next year. Thank you. And this is the feedback from my students. The class is extremely useful and rewarding, amazing addition to the curriculum, really useful, building strong communication skills. It was clear we improved in this. Okay, so last 5 minutes I will talk about what I've learned during the pandemic, which was teaching to little black squares with names on them. It's horrible. Not what any of us signed up for. Soul destroying. We got through. But what I did learn from the pandemic is that I now actually, finally, after some 20 years of being in the classroom, I finally flipped my classroom. So this is in the second year electricity and magnetism course. So before the pandemic, it was it wasn't. They had reading assignments to do, and then we did some stuff in class, and they would work on problems together. So they had a reading quiz weekly, and then they had assignments, and they had a midterm, and they had a final. And then I did not want to figure out Respondus or whatever else in terms of doing an online exam, so I didn't do an exam in second year E&M. Didn't do a midterm, didn't do a final. What they did was they did a portfolio or a personalized study guide. So what that was, I broke the course up into themes, like say for example, use symmetry to simplify a problem, for example, in second year E&M. So explain that concept to me and give me 3 problems that you've created that are not problems that we did in class that you have worked the solution to. And that was what they did for their final assessment. So then this is what it looked like, or part of the classroom looked like. So this is the second year. So the first year was talking to Zoom with nobody talking back. But trying to engage. And then the second year was hybrid. So I had students physically in the room, but I also had a conference enabled lecture space. So we had speakers in the ceiling, so students who were online could talk to the class and could hear everything. And they were joined on Zoom, so they could chat as well. And we used that time to work together. So after the first year of the pandemic, so I've taught second year E&M off and on a bunch of times over the last 20 years. So I finally was like, okay, fine, I'll write up my lecture notes. So I took my lecture notes and I typed them up, I put them in Word, and I gave them to the students like a few pages at a time. That's what they had to read before class, and then we worked together. That was the first year of the pandemic. All good. Then the summer, after the first year of the pandemic, Top Hat took my Word document and put it on their platform, did all of the formatting, all of the equation stuff, all of the images. It was a lot of work for them, so I was very appreciative that they did it. And then what I did was the problems that I would normally do in class, which I did the previous year in class, and I've done lots of times, didn't have the worked out solution to. I took the video recordings from the previous year where I taught on Zoom and recorded everything, and I took the 5 minutes that I had worked that solution, and I cut it, and I stuck it into Top Hat. So here's all the theory, here's the problem that I would normally do in class, here's me working that problem, and then they have a check your understanding question that they have to do that is going to get them grades. So watch the video, read the stuff, then the question is like, okay, in this question, let's pretend instead of this, I did this. It's a charge distribution that changes linearly along or something, right? What happens then? And then that's their check your understanding question. So then the time in the classroom is really what the whole flipped classroom idea is, working together on problems. I've talked about this with a few people already today. it's the devil's in the details, like everything else about how you deliver a pedagogical approach. It's really important how you structure things. The feedback from the students, it's not a large number. It was a small group and not a lot of them did the online feedback, but the feedback from the students was they enjoyed the discussions, they found it useful, they found the material, the textbook helpful to their learning. Won't worry about that. The issues with the portfolio. So I learned a lot on the first year of doing this. So the first year I broke the course up into themes, and they had to submit their thing at the end of the semester, and it was worth like 45% of their mark. And I was like constantly like, don't forget, you need to be working on that study guide. And did they work on that study guide until week 12? Of course they didn't. So there was a mad scramble at the end. These were big documents, and it was a lot of work. So that was a huge issue. They left them till the end. They were stressed about it being open-ended, and they didn't understand the nature of it, so that was hard too. I basically solved all of the issues in the second iteration by making them due in installments. So they had one chunk that was due at the end of the first 4 weeks, next chunk was due the next 4 weeks, and then the last one. So less stress, more time in advance doing it, plus they got feedback from us about what was expected on the first one, which was only worth 15%, and not this thing that they submitted that they didn't know and it was worth a lot, and so it worked out. And definitely the feedback from the students was, I think it worked well. Their perception, so this I've asked them, I've followed up with the students now just recently, a few months ago. So these are students who are now in 3rd and 4th year. So this is over the 2 years that I did it this way. And what I love to hear is that they were actually going back to their study guide that they created in 2nd year E&M before they started 4th year E&M to review. I'm like, wow, that's amazing. So they found it useful in terms of motivation. They found it useful in terms of they felt a better understanding of the material. So all in all, I'm going to continue to do it that way. And I know it's 2:30, and I'm sorry, I know we started a bit late, but I will wrap up here. These are all the ways to find me, and I'm happy to take questions.